This is a Canox Starpower 300 welder, which is basically just a rebranded and repainted Miller XMT 300. These are DC output MIG welders. They can do stick as well. This is the second time I see this unit, which is kind of annoying. A couple months ago it had blown the fuses, and I replaced the main bridge rectifier here and a couple things. I think there was a blown fuse here. This resistor was just cooked, and I couldn't find anything else wrong with it. I worked for a couple weeks, and well, you can tell it doesn't take long for these to get filled with dust and crap. This comes from a metalworking shop where they do a lot of grinding, and the first time I got this, it had probably never been cleaned. It was packed with metal grinding dust like this. So it's a pretty good thing they have this conformal coat on all over the circuit board, because this is just filthy. I'll take a closer look, take a couple measurements. It might be these I think they're film capacitors. They do a lot of work, because I think the whole thing is a resonant system where these caps, there's two on the other side, and there's a bunch of coils in the bottom section, and these IGBT modules, one on both sides, they do some sort of resonant thing I'm not too sure about. But I'll see if I can look at these closer this time. I'm assuming the diode bridge blew again, which is annoying. They're kind of expensive. By the time I had this machine in my shop and had the covers off, it had been powered off for quite a while, but still I checked various points here, especially near the bridge rectifier and the IGBTs, to make sure everything was discharged to a safe voltage. What I did next was to look at the input bridge rectifier, and sure enough, one of the input diodes was shorted out, but I could still use the other two inputs as a single phase bridge rectifier. This was useful for troubleshooting, because if something went wrong and I destroyed this one, well, at least it didn't cost me a brand new $80 part. Next, I looked at the IGBT modules. Each brick like this contains two IGBTs, and well, it's a bit painful to watch because I didn't notice the pinout was molded into the case, so I was trying to figure out which is the common pin and what combinations are supposed to read as a short circuit. The area I'm looking at for these tests is near these IGBT modules. I'm looking at the gate drive signals, so gate to emitter, if I disconnect this temporarily, gate to emitter should be an open circuit. This is an insulated gate, that's why they're called IGBTs, and there's not supposed to be any contact there. Same thing between this gate and this emitter. And these are the small contacts, red, white, white, red, white, red, so those are the smaller wires. But one of those, the emitter, is also wired to the common terminal here, so that's why some of the measurements I'm making read as 0, like between the small red wire and the common terminal. That's normal for it to be 0. And on the other side, once I disconnect this, I'm measuring the circuitry here, and I'm not expecting 0 ohms. What became obvious after a bit of probing was that both IGBTs definitely had issues, and also when measuring the control board with nothing connected, I had different readings on 2 or 3 of the channels. I'd expect all 4 drivers to be pretty much identical. I was just poking around at this IGBT, and I noticed this flap looks like an access port, but it's not. It just that's the side of the IGBT. Holy crap! Okay, it's probably safe to assume this is not normal. Right, so I flipped the machine back on this is the right side, and what do you know? Well, this might be hard to see, but it's got the same flappy side thing going on. So they both died. Interesting. And by the way, these screws, when they have the dot, that's usually they're not Phillips and they're not posi drive. It's JIS, the Japanese standard, which is not too surprising on this. These are Toshiba IGBTs, and I don't have JIS screwdrivers, but it doesn't matter because these are going straight to the trash. Okay, so I just very quickly traced the gate drivers. There's 4 identical sections. That's good. And so there's the coil here. There's a small resistor here. I think this one is 10 ohms. This one is 100, I think. Hard to see the colors through the conformal code, but it doesn't matter anyway. And 2 back-to-back diodes. One of these, or maybe 2 of them, are zeners. I think they're probably both. And I just started probing around, and I already see problems. Since there's nothing connected here, I can probe these individually, and the coil, the low resistance of the coil won't affect the measurement unless one of the diodes is shorted, in which case I'm going to measure at 0. So let me see. So I have 8 diodes to test. This one's not exactly 0. He's either I might be measuring the coil resistance through the shorted diode. I'm just gonna remove all of them, or at least yeah. If I remove one of them, I open the circuit and then I can measure the diodes properly. But I'll probably end up replacing all of them. If I'm thinking if the gate's shorted out on the IGBT. I mean, this thing runs on 600 volts rectified, which means that's what, 900, yeah, not quite 900 volts. So if the gate shorts to the emitter, I mean, there's going to be some pretty serious voltage going on here. I hope the only stuff broken is these diodes here. I don't think a spike could really feed through the transformer here and cause damage on the other side, but I can see the MOSFETs, the low side, well, not the low side, but the primary side MOSFETs. I can find them pretty easily, and I can see if they're open or short. And I'm going to assume most of this board is okay, and just look at the diodes. I just finished removing 8 zener diodes from those gate drivers, and there's 5 that were dead short and 3 others that were open. The resistors look okay, both sides. The coils, as far as I can tell, they're probably okay, at least not open circuit. And I've just traced a bit how this works. Yeah, it'll be maybe clearer like this. Those are the 4 transformers, and 1 and 3 are on one side, and 2 and 4 are on the other side. So they're driven from the same MOSFETs, Q4 and Q6. Those are the 2 here, and their source goes to Q8. That's the 3rd one in this little group. So I don't know, maybe are they doing some kind of PWM here to control both? And I don't know, it probably doesn't matter at this point. There's nothing else for the moment that stands out. I checked a couple of those capacitors. They all look reasonably fine. Oh, this connector here, that's for the auto link relay, and it's driven by this transistor here. It's just an NPN, and it's not shorted. I didn't look at all the logic controlling it, but it's probably okay. There's definitely at least a few different variants and versions of this depending on their input specs. For example, this one is a 230 and 460 Autolink model. There's the 460 and 575 volt model, which is what I have. At least some of them were built for single voltage operation, which makes them a bit simpler. But in any case, you got to take the schematics that are glued inside the top cover of the unit, because those are definitely going to be the most accurate. So I opened this one just to illustrate how the auto link works in the power section. So there's a lot here, but most of it doesn't matter for our discussion. So I'll start here at the bridge rectifier. This is where you start getting DC, rectified DC. So you have positive voltage going into the top of this IGBT module. Then there's a contactor here, W2, and W3 here, which is probably the pre-charge, I think. I'm not certain, I've never seen this unit. And it feeds the bottom part of the right IGBT module. Now if you're hooked up to 230 volts, then W2 closes. WT here, so these two contacts, they close, so you end up with your positive voltage at the top of both IGBT modules and the negative voltage to the bottom. So they're both working in parallel. And if instead you're hooked up to 460 volts, then this is what you get. W1 closes, and W1 stacks both IGBT modules in series. So your positive voltage only feeds the top of the left section, and the bottom of it only goes to the top of the right section, and this one's hooked up to the blue one. I've just redrawn this, restacked it to show better what I mean. Okay, it's the same schematic. I just moved stuff around and erased most of it. So in 460 volts operation, and you have the positive rail up here, and then it's connected in series with the other one. And because of these capacitors, these are the big blue ones at the bottom, the bulk capacitors. I think they're 2800 microfarads. And because of these in series plus these resistors to equalize the voltage, you end up with half of the supply here and 3/4 here and 1/4 there. Here's the input section on my machine here, but the other ones are roughly similar. So what happens here is the front panel switch is S1 here, and when you turn it on, this is the main contactor, but it doesn't turn on immediately. The first thing that happens is L1 goes through this resistor here and sort of bypasses the contactor, and then L2 does the same thing through this fuse, another resistor, and like this. And line 3 doesn't make it to the bridge rectifier yet, so you're only feeding at one phase and via two resistors. And what this does is it allows the bulk capacitors to charge at a reasonable rate. And then for this contactor here, W, it's controlled from the main control board here, and it's just a fixed delay. On mine it's about 6 or 7 seconds after power on, then it closes W, and then, well, line 2 makes it directly, and same thing for L1. So these resistors don't matter anymore once the main contactor is energized. Next, on my unit, on the 460/575 volt versions, the power sections are always stacked in series, as I was showing, but there's still an auto link relay. It's CR1 here, CR1, which is mounted close to the fan on mine. It's also controlled by the main PCB, and the way this works is from this winding here, which provides plus and minus 24 volts. If the control board detects that it's not 24, then it will energize CR1. So by default, when you power it on, to be safe, it assumes that you hooked up 575 volts to it, which means line 1, which feeds this control transformer. So line 1 goes in here through the normally closed contact, and it energizes the longer winding. If on power on it does this, but you were only running 460 volts, then the the control board detects this condition, and then, as I said, it energizes CR1, which means these contacts, this one opens, and the other one closes. So then you're feeding the transformer from the shorter winding, which means then you'll get the proper 24 volts. Troubleshooting a machine like this that runs, that's designed to run on pretty high voltages is quite dangerous and a bit tricky, because you can't just go feeding 600 volts and just hope that everything works, because if something doesn't work, like let's say the control board is energizing both IGBTs at the same time, here you just short out the whole thing and that'll just destroy absolutely everything on its path. Both IGBTs are going to die, the bridge rectifier is going to die, probably long before your disconnect here, which is hopefully fused or at least breakers. Before that opens, you'll already have caused damage. But what you can do on this unit, well, on most units, I think they're all designed with this same idea. There's a primary side and a secondary side, I guess. So what I mean by this is the primary is where your mains comes in, so L1, 2, 3, and you have an isolation barrier here through this transformer, so all the primaries on this side. And the other one that's less obvious is on this control board, these gate control signals. There's 4 of them, a gate emitter, gate emitter. Well, on this side of the wire, they're on the primary side, because this one here is mid voltage, this one is sort of 3/4 voltage. But inside here, I just changed views. This is the schematics. It's part of the schematics I traced for the control board, and the emitter and gate signals that I was just pointing out, they come in on these connectors, RC18 and 28. And, oh, I never wired them, but here they are. They just go like this. And there's 4 control transformers. So this provides your insulation between the primary side, which is on the right side here, and the rest of the logic. Back to the overview here. So these we know are insulated right when they come in on the board. Same thing for this one here. Next, this looks kind of suspicious, but this is just a current transformer, and it's by design it's isolated there. And I think this is I didn't look closely at this, but I think they're just on the same core, and there's one winding. I'll come back to that later, maybe. These two, that's the output voltage sense. Oh, it's hard to see here, but those are the output terminals. But those are on the secondary side, because you have this other huge transformer here. Weird windings on it, but you do have an insulation layer here. And on one side, you have the output here of your resonant converter. So this also provides isolation. Where was I going with this? Yes. So that means this whole side, the whole power section, can run on its own. If you break this here and this here, then you can feed this low power section. It's still high voltage, but it's low power because it's only running a fan, the PCB, a couple other things. And then you feed whatever you want here. So I started really low, 10 volts. There you go, 10 volts here, 0. And well, that wasn't enough. But it was enough to demonstrate that these weren't shorting out and the control board was working fine. And I increased this to about 40 volts and so on. And eventually I hooked up, that's all DC of course, because I'm bypassing the bridge rectifier. And eventually I reconnected these two to the bridge rectifier, but then I fed 120 volts AC to L1 and L2, because this machine can run perfectly fine on one phase as long as you hook up only L1 and L2, and as long as you derate the output, because obviously everything's working much harder when you're only feeding one phase. with 120 volts, the open circuit voltage on the output was only about, I think it was around 10 volts output. But still, at that level, I could short out the output, like directly just bolt the welding cable short-circuited, and with that, I was able to go up to 55 amps, and I could make sure that all the controls worked and nothing was going wrong. And then 240 volts. That was almost enough to get some welding action, but not quite. I really had to go all in at 600. If you don't have 600 volts at all, then it's kind of tricky. Well, no, not tricky, but it needs a bit more work to power the control section, because this winding kind of wants 600 volts or 460. Or this fan, it doesn't say so on the schematics, but you can tell from the part list. This one's designed to run on 240. So what you could do is disconnect a bunch of stuff, disconnect the fan, and feed 240 volts from here. It's not great because you're bypassing the power switch, you're bypassing the part of the pre-charge, but by feeding 240 volts on this winding, you make sure you're actually producing 602, so you got to be careful with this, because this is going to be at 600 volts, so you'll also have to disconnect either here or wherever's convenient. But the idea is to get the proper voltage on one of these windings. Heck, you could even go on this side and hook up 24 volts AC, just as long as you make sure it's AC obviously, or 120 to this winding here. Any of these will work for the low power section, assuming you disconnect this too, either on this side or the other one. When you look at this circuit a bit closer, you notice there's one current transformer here, which is really inside the resonant converter loop, and there's another one on the output here. This one is a big one on the top of the unit, and it's fed from plus 24 and minus 24 volts DC, and the signal comes in here on RC12.6 on this one here. And this one is the one that's actually used for the main control loop, if you will. So this one will follow your the main dial if it's set on CC mode, or if you're in CV mode, it still needs this signal. Reasons are complicated, but depending on your arc control setting, it needs to know what the current is, so it uses that signal all the time. And it also sends it to the digital panel meter. It's one of these here, doesn't matter. So this one is really measuring your output current, whereas this one here is only for the switching logic, because these need to switch at particular times, which are a function of where it is in the current. So it's going to be switching square waves here on this side, but then when this resonates, you end up with sort of sine waves like this, more or less. I'm not pro at this, it's a pretty interesting topology, but anyway, this is used to detect the zero crossings here, because that's when you want to do your switching. Well, that's a rough idea. Then these diodes right here, they were bugging me a bit, so I just I redrew it on a piece of paper, which I lost. But these diodes are nothing fancy. They simply go between roughly like this, the other one like that, and they're using bridge rectifiers just to get those two parallel diodes, make them a bit more robust. And this is just a flyback protection for both these switches. They do have a built-in diode, but I think that one's just a side effect of how they're built, and they're not really designed to take all that abuse, because this is a pretty hefty welder. These pots, those are your panel controls. The arc control is actually ganged, so this is the same pot. So both sliders move at the same time. Now what I'm doing here is testing the film capacitors, which are the two big ones there, and on the schematics, these, so one for both power sections, and I'm applying about 70 volts DC and measuring any leakage current, which would only tell me if it's really bad, defective, or if they're very different, but it doesn't guarantee that they're still good. And with this this setup, I'm going to try to look at the resonance of both those capacitor and inductor sets. From what I understand, they need to be pretty symmetric, so I'm going to try both. I'm not looking for any absolute measurements. I'm just looking to see if they match up. Yeah. Wiggled some connection accidentally. Interesting. Okay. But in any case, it's pretty. I don't think this is going to cause any problems. After that, I ran some tests on the 4 bulk capacitors in the bottom there. I measured ripple, I tried to measure ESR at higher power levels to see how they behaved and to make sure they were nearly identical. It turned out to be a waste of time, but that's always easy to say after. Plus, I was waiting for parts anyway. Next, I checked the gate drive signals coming from the control board, and everything seemed okay. And finally the IGBTs showed up, so I was able to run low power tests feeding the power section from just a DC power supply. Alright, so I increased the DC voltage. I actually put two DC power supplies in series just to get a bit more voltage, because it seems that's the main limiting factor. I got the machine set up same as before, my clamp meter, and 14 amps, and I'm reading 14 on the meter, so it's good. So at least there's 2 current sensors, one for the control and one for the front panel. One of them is good at least, probably both of them, although I'm surprised that even at the lowest setting, which should be 5, it's giving me 14, and I got all this set to front panel. Yeah, no, that's nothing. Okay. I wonder if it's just not getting its current feedback, or if this is just too low a voltage and it can't do its thing. I'm not too sure. I was sort of on the right track with this. I found out much later that it has to do with the arc control panel setting, and the answer is there's hints in the manual. It says arc control for CC mode, constant current, provides variable selection of short circuit amperage to suit welding situations. What it does actually, how this is implemented, is the current that the welder tries to provide is a function not only of your panel setting, but also the arc voltage. So in this test at very low powers that I just did, or when it's short-circuited, the voltage is so low that the welder is trying to compensate that low voltage because it thinks it's a short circuit, and by increasing the output, so increasing the current, it's trying to break that short circuit, which is what you'd want if you're stick welding. But it's misleading when you're trying to figure out if the current control works. So the solution was to back off the arc control all the way to at least 0 or 10%, counterclockwise all the way. And by doing that, then the panel control works as expected. Right, so this board, there's a bunch of 4000 series logic ICs in a bunch of places, and those usually run with up to 15 volts. And since I was getting 15 volts on the gate drive, I figured that'd be the power supply. So I probed around and I could see the 15 volts, plus and minus 15 volt rails, so that was fine. There's also some plus and minus 24 for at least the current sensor here, and this one drives the front panel. I'm now fairly certain, because when I disconnected the reading, that goes all the way to 0. So I messed around with those, and then I went to the back here where there was this, it's a 150 ohm resistor, and it was pretty toasty. The conformal coating was all baked around it, which isn't necessarily sign of a problem, but still caught my attention. And these two optocouplers here, just through the fun of it, I probed them with the multimeter, and on the right side here they both read as shorts, and I find that a bit strange because even with all this stuff connected, if it was, I don't know, if it had been driven directly from a transformer winding somewhere, which I don't see but never know, that could explain the 0 ohm reading, but looking around I can't find anything to explain this, so maybe these two optos are burnt. If that's the problem, that's really interesting because that's a whole other area that I haven't looked at all. And wrong on both points. The first one, well, it took a bit of digging to find out, but this is part of the circuit. This is that resistor that seemed to be burnt, but it really wasn't. This is part of the main contactor coil driver. This is an SCR, and they're driving it pretty hard. They have this, they're taking the 15 volt rail. This is a P-channel MOSFET, and just 150 ohms, so that's, what is that, 100 milliamps. So they're really driving this track really hard, and that's it. That's all. It's just burning, I think it's about 1 watt or 1.5 watts. And that's plenty enough to explain the charred conformal coat. And for the so-called optocouplers, the answer was, but just looking at it closer, I could see the IR logo on there. And if you go in the old early 90s catalogs, you can find these hex dips. And they look a lot like those 4-pin dips that are usually optocouplers, but the drain, this is the drain connection, and the pins are, it's the same metal tab, but it was hard to see with the conformal coat, so I actually didn't notice. They were just the very same thing, so false alarm. My next steps were pretty tedious and not very interesting, plus I didn't film anything because I wasn't going anywhere and not fast. I checked a bunch of things. At some point I suspected some of the panel controls because I hadn't figured out that arc control setting yet, and everything checked out fine. Back to the PCB, I looked at some of the current and voltage signals. It's a pretty complex board. It's hard to navigate without schematics. One of the ICs, the one right here that I removed, it's an analog switch, and some of the pins around here, pins 14 and 15, it looked like they were getting shorted to ground in certain conditions. So I popped it out of there to test it in the breadboard on its own, and it was fine. That was not the problem. It's just how the circuit operates. So I threw a brand new one in there. So instead, since everything seemed to be working at least somewhat correctly, I just increased the power supply. And then I figured out that current control setting. That gave me the confidence to wire it to 600 volts. And you can see it here, it's working fine.